This is Monday, January 30th, 2017. I'm Cindy Kelly, Atomic Heritage Foundation, and we're in Washington, D.C. with Bruce Cameron Reed. If you could say your name for us and spell it.
Bruce Cameron Reed, BruceCameronReed.
Great, terrific. So, Bruce, tell us about yourself. I mean, I know you're a professor at Alma College, but maybe you could start at the beginning, just like, when and where you were born and how you got interested in science.
Well, I was born in Toronto in 1954, and I guess as a kid, it was the height of the space race. And I can remember in grade school, watching John Glenn and Alan Shepard and all these guys, and it was, so exciting and exotic. And I guess that, spurred an early interest in science. I was a classic kid science geek with his little telescope. And so there was that space, influence. When I became a university student, I studied astronomy and physics at the University of Waterloo in Ontario, and they had a very strong physics program. And so I eventually did my PhD there. And when I began my academic career, I was doing sort of conventional astronomy research and teaching physics. But always in the back of my mind had been this just interest in this history. And this may sound a little strange, but I can remember when I must have been about 8 years old during the Cuban Missile Crisis. My father had a darkroom in the basement of our house. And I remember my parents outfitting this little darkroom as a bomb shelter. And so that was just part of the culture then, of course. And, at that age, it seemed like some sort of an adventure, but they must have been scared out of their wits. And so anyway, that interest, I guess, was always in the back of my mind. And, as a physicist, you can't help but be interested in this sort of thing. And I guess like so many people that come to this, I read Richard Rhodes's book when it first came out, and I just thought, I want to learn what is the physics of this. How does all this stuff work? How do they calculate this stuff? What's the relevant physics? And so I just began slowly reading papers, reading journal papers, digging out my old nuclear physics textbooks, and began calculating things. And then, as this built up, I realized that so much of the physics that underlay nuclear weapons is actually quite understandable to a good undergraduate physics student. So I began publishing some papers in physics journals and contacting people, and then you realize, well, it's so much more to it than just the physics. You can't separate the physics from the historical context and the people involved, and so you can't help but get interested in all these other aspects of the project as well. And I tell my students it's addictive. I began just being curious to know, how do they calculate a critical mass? Well, and then it kind of blossomed, and because every aspect of this thing connects to so many others, and you can't just pull them apart one aspect at a time. And so it just kind of grew from there and became I was lucky in the sense that I could let it become a professional obsession and publish papers on it and go to conferences and write books and just speak with people that were involved in this. And there's always something new to learn. It seems almost infinite in its aspects. So I guess that's how I came to be here.
It's wonderful. So tell us what the span of the courses that you're teaching at Alma College now.
We're a small liberal arts college, about 1,400 students. So my mainstream everyday work is traditional physics classes, everything from a first-year physics course for pre-med students up to our senior level quantum mechanics class. And there's only 3 of us in the department. And so you end up, over the years, teaching essentially everything in a physics curriculum, pretty much. And which has its advantages, because it lets you, I think, over your career of doing that, see the connections between those things in a better way that you probably appreciated when you were a student yourself. And you can, because you keep dabbling in all those areas, you can build the connections. And then specifically, when I began getting interested in this Manhattan Project material, I guess now about 20 years ago, after a little while I realized this would be the perfect topic for one of our general education classes. Every student, no matter what their major in the college, has to take a physical science class. And so there's the usual things like geology and astronomy, and so I just proposed putting on a class on the history of the Manhattan Project and the relevant background physics and this sort of thing. And so I do that typically about every 2 years, and it gets a lot of history students, political science students that have to get a science credit, a physical science credit, and they just find that's kind of, looks relevant to their interests. And I'm sure you know this, that our present generation of students, many of them have no idea of the history of this, of the historical context, who was involved, what was involved. So I guess I've come to see it as kind of a, not only teaching them about the physics and the context and but doing a kind of a public service in bringing some of this knowledge to this generation.
So what is the most important kind of takeaway from the Manhattan Project that you hope your students absorb?
Wow, I think that's a hard question, because there are so many aspects. I guess, one is that you can accomplish such work of enormous complexity, with competent people running it, being allowed to appoint competent people, to do the jobs. And many students are surprised to learn that this wasn't just a couple of guys sitting around a coffee pot deciding to invent a nuclear weapon. That there was a long history of underlying discoveries. When I begin the course, I begin with the discovery of X-rays and radium, and we sort of build up through some of that 20th century physics history, and that this was by no means, preordained. Nobody anticipated the discovery of fission. A lot of these discoveries were just accidental, serendipitous discoveries that, then kind of accumulated to the point where when nuclear fission was accidentally discovered, within weeks, a number of people recognized that this was a possibility. It would be extremely difficult. And then I think they're often surprised at the vastness, the complexity of the whole project, that so many hundreds of thousands of people were involved. It cost so much money, but it was kept largely secret, which I think would be impossible today, because everybody would have their cell phone, inside a factory somewhere. And that it also, and then when we come to the part of the course that deals with, after they had worked through the many, many challenges of getting working designs for these weapons, that these weren't just willy-nilly dropped, somewhere in Japan, that very serious people were giving serious consideration to how would this affect the geopolitical strategies, the target committee, the interim committee. This went up to very high levels in the government, and it was being taken very seriously by very serious people, and wasn't just some willy-nilly decision. In the entire context of the war, I think, is a surprise to many of my students. They have no, in many cases, no idea of just how ferocious the war had become and how long it had dragged on, and the idea that a prospective invasion of Japan would have been just horrific had these bombs not come along. So I guess there are multiple takeaway messages that, the vastness and the complexity of these things, the organizational challenges and the technical challenges, I guess if you look at it in retrospect, any one of those things could have derailed the whole thing. There are so many ways this might not have come to fruition with all of the complexity and difficulties they ran into, but they did succeed in making it work.
I'm glad you said that, because I think that especially students today, and you read the book and you know what happened, and it just all seems so inevitable.
It was far from inevitable.
Right. So what were some of the challenges? I mean, I invite you to talk not just about technical challenges, but you mentioned organizational challenges. So what kinds of things?
I often wonder if we say compared to the present day, the organizational challenges of if an equivalent discovery of such potential import were made, how would information on that be gotten to the relevant decision makers? And so the architects of this were very fortunate in that they had very competent people, competent engineers who had the access to people like the president to make them aware of the potential of this. And then, when research began getting organized, it was very disparate. It was in a number of universities and industrial labs across the country. So this had to get put together coherently, to avoid overlap, but also keep some compartmentalization in things, because there was really so few people at the top of the heap that really had a comprehensive view of the entire enterprise. And so those people faced enormous organizational challenges in keeping all these balls in the air at once. And I think, to my mind, the person that's always underappreciated is General Groves. He was remarkable. I mean, Stan's description of him as the indispensable man. And I think before I really began to dig into this, you get influenced by the Hollywood versions of this man as a bit of a blowhard, or something like that. But he was a very smart, dedicated, hardworking man who just must have worked tirelessly, for 3 years to bring this to fruition, and to organize one activity like an Oak Ridge or a Hanford or a Los Alamos or a CP1 would be a job for anybody. But to keep all of those things running in parallel, solving their problems simultaneously, I think is really remarkable. And done, in all of the documents one reads and financial reports and everything, and there's never a hint of anything, not a penny improperly spent, of $2 billion. Imagine that now. And yes, there were areas of research they pursued that turned out not to ultimately be used, but of course they couldn't know that before they started. But I've never had a sense in anything I've ever looked at that anything improper was done in such a vast enterprise, which was being kept very hush-hush.
That was great. I'm just pausing because there are like a million different avenues to pursue. Thinking about innovations in a technical sense, then, can you give us one or two examples of what you think?
I think many.
Good. Give many, then. Just don't stop.
Thinking about this when you were speaking with John. and this is going to probably, be biased by my own physics background. I think he alluded to some of the developments, in high-speed electronics for triggering the bombs. In the testing of the implosion bomb, they had something like 6 different diagnostic tests for the symmetry of the implosion. And some of these were incredibly ingenious, like as something would implode, they would have electrical wires inside the assembly, and the resistance would change as the density of this material changed. And by monitoring an electrical current, you could measure the symmetry of the implosion. And I think nothing like that had ever been done before. So imagine you have as a professor would say, consider a spherical lump of plutonium, about the size of a softball sitting in my hand, and to trigger the nuclear explosion, this has to be compressed to a higher density. And so then the issue becomes, how do you compress a metal maybe to half of its initial volume? This requires an enormous amount of pressure. And the technique they developed for achieving this was to essentially wrap it in segments of explosives in a 3-dimensional assembly. Think of sort of pyramid-like chunks of explosives that would fit together like a 3-dimensional jigsaw puzzle, which when detonated would blow inward to crush this thing. And there were 32 segments surrounding that core altogether. And given the speed of the explosive, they all had to trigger within a microsecond. So the simultaneity of the detonators, and if the implosion is, say, a little off-centered or asymmetric, the core might shoot out one side, or you get an uneven density compression, and you get a much less efficient nuclear explosion than what you were trying to design for. And so they invested an enormous amount of effort in getting that symmetry correct, even to the point of testing things such as putting radioactive sources within a test implosion assembly. And as that was crushed, radioactive material would be released, and you could monitor the radioactivity as this thing went through its microsecond operation. And then, so these things had to be monitored on that time scale. They developed X-ray cameras that could operate at microsecond exposures to actually image the implosion. So I think all of these huge developments in electronics and high-speed photography and this sort of thing, all those diagnostic tools for developing that weapon was really remarkable. And I think along with that, sort of on the theoretical side, was there had probably been no project, no scientific work prior to that that used computation to such a degree as they did to, in the days before everybody had a computer on their desk, trying to write an algorithm to simulate an implosion, or what happens once the reaction is triggered. And so people with slide rules and primitive electronic calculators doing these sort of step-by-step simulation calculations, in 1 nanosecond step at a time to simulate the progress of the explosion. And of course now computation is, such an integral part of anything in the sciences, but that was really revolutionary at the time. And using primitive punch card machines, basically tube-driven computers which would take hours to run a simulation that would now be done in milliseconds, or take them weeks. And so the whole development of computational physics was a huge enterprise, at the time. We take it for granted now, but it was enormous. Some of the techniques for enriching uranium had never been done on a large scale before, like the gaseous diffusion. When originally developed, one might get micrograms The first isolated samples of uranium-235 were nanograms, smaller than the head of a pin. And some of these techniques then had to be scaled up to get tens of kilograms, and almost literally separating uranium into its constituent isotopes atom by atom, and being able to do that on a scale large enough and quickly enough to isolate enough material in a year or two, to make one or a few weapons. There'd never been such an industrial infrastructure. And carrying on from that a little bit, I've never tracked down this figure, and I assume it's accurate, but I remember reading somewhere that the capital investment in the factories, in the plants, was equivalent to the automobile industry of the time. And so the contractors built an infrastructure equivalent to the entire automobile industry of 1940 in about 2 years, and made it work. I want to get a student to go back and check the stock prices of all those companies in 1940. And these facilities were built so well. Hanford, the original Hanford reactors operated into the 1960s. And they were still operating, but had been eclipsed by larger ones. The gaseous diffusion plant operated until 1985. And some of the calutrons into the 1990s. And so these things were built, they lasted half a century almost. That's a really remarkable undertaking for something that had never been done on that scale before. I don't know if you would put this under the heading of innovation, but probably never before had there been, such a marriage of science, sort of scientific research, industry, and military engineering to such a degree that these rather disparate entities, these academic scientists and researchers, then within the culture of the military hierarchy in engineering, and then the entire culture of the industrial engineering people, the chemical engineers from DuPont and Westinghouse, used to large-scale factories. Probably very removed from the beautiful, pristine calculations of some physicist put into practice on that large scale. And so just, those are very different cultures of people. Academic scientists, industrial engineers, the military, coordinating these very different cultures was probably an enormous challenge in itself.
So also you mentioned the challenge of the pristine theories meeting the messy realities.
The practical reality.
Yes, exactly. So can you talk about the relationship with the scientist and the engineer? I mean, that's sort of on that theme.
Yeah, of course, many of the folks viewing this video will be familiar with the fact that there were criticality accidents at Los Alamos. Of course, a good physicist can calculate a critical mass for uranium-235. But they had to test this in a laboratory by, bringing close together two pieces of enriched uranium, and yet not letting them get too close together. Monitoring the neutron flux as these things got closer and closer together, and then extrapolating that laboratory experiment, to an entirely assembled system. And so the calculations weren't just relied upon solely. The people doing hands-on experiments with these very dangerous materials to actually test these theories. And then they would make these larger and larger critical assemblies as more and more fissile material came from Oak Ridge or Hanford, and they could more closely approximate a finished critical assembly without actually getting there. And that is dangerous work. These people really had to know what they were doing. And I cannot imagine just standing over an assembly of enriched uranium that is so close to critical that if I lean over too closely, my body will reflect enough neutrons back if I get a little too intimate with the thing to induce criticality. They were that close. So I think it's kind of amazing to me that they didn't have more accidents. There was a culture of safety consciousness, but also that drive that we have to do this, we have to get this job done, and didn't have time, I guess, for elaborate precautions that would be taken now.
Yeah.
Well, when one envisions a person holding a plutonium core or a uranium core in their hand, it's rather remarkable to me.
Have you held one?
No, I have held a cubical lump of pure uranium metal, which came from one of Werner Heisenberg's reactor experiments. And so it was unenriched uranium metal, but you could tell it had been machined, and deliberately machined. And it's a little cube, it weighs about 5 pounds, and you just have this sense of literally holding history in your hand with something like that.
So it was little, but it felt pretty heavy, I bet.
Yeah, it's about 5 pounds. It would easily fit in the palm of your hand. I can show you a picture later. It can be fascinating to view some of the artifacts of those. I was thinking of some of those innovations, and I'm sure you've seen at Los Alamos the implosion lens molding machine that is in the Bradbury Museum. And so here are these people making these casting molten explosive into a mold in a commercial candy making machine, and then casting thousands of these, taking them out, perhaps holding them in their laps while they machine off the rough edges of a cast explosive to make sure it all fits together accurately. And to see some of these artifacts when one gets into this, and to touch some of these things and think of who was involved in this, who would have been there and seen this stuff and used it, and what the contribution it made can be quite striking.
There's I don't want to derail us. There's lots of good stories about there are a lot of good stories about Kistiakowsky with his, just what you were saying, trying to shave off the explosive lenses. Yeah. And Rhodes asked him, what happens if when you're sawing this you accidentally cause it to explode? And he said, well, I would never know.
No. They worked with non-conducting tools. They would, to maintain the symmetry of the implosion, these cast chunks couldn't have air bubbles in them, so they would X-ray all of them. If there was a void inside, they would drill into it with a non-conducting tool, rather like a dentist, getting to a cavity and then melt a little more explosive and pour it in there to patch it up. So these were literally handmade. These were handmade nuclear devices. Every component fitted together by human hands, and taped together, and it wouldn't be like manufacturing widgets on an assembly line. All pieces, assembled by hand. Can
you talk about the initiator? and what that did and how that was made.
I guess what I can give is what I have read of speculation, because apparently there's just still a very highly classified, the actual structure, a very highly classified device. The initiator was apparently about a golf ball sized sphere at the very core of the weapon, which, when crushed by the arrival of the projectile piece in the uranium bomb or the implosion in the plutonium bomb, would emit neutrons to trigger the nuclear reaction. And the physics of this, how it operates, is in any textbook. And there's a process that if you have a radioactive substance that is an alpha decayer, so alpha decay has been known since, so Ernest Rutherford in 1902, but there are some elements such as polonium that are very prolific alpha emitters. And an alpha particle, if it strikes a nucleus of a light element, such as beryllium or aluminum, will tend to emit neutrons. It's called an alpha N reaction. It was involved in the way James Chadwick discovered the neutron in 1932, ironically, and then I often wonder what he thought. That was how he, such a reaction was involved in his discovery of the neutron. And 13 years later, he finds himself at the Trinity site, seeing what his neutrons could do. And so what one would need in one of these devices would be then a sample of something like polonium, some layer to separate it initially from the light element material. I understand beryllium was used so that the alphas couldn't penetrate that little protective layer before the bomb is triggered. But then when the triggering goes and the device is crushed, the two materials mix. And you can do a rough calculation from estimates I've read of the number of grams of polonium there, that in the sort of critical microsecond of assembly, you get about 100 neutrons to then trigger the nuclear reaction. So these were very tricky devices because the polonium has a short half-life. I'm trying to remember it off the top of my head, but 130 days. Okay, and so they have a limited shelf life. You would have to keep producing this stuff, which was produced in the reactors at Hanford and Oak Ridge. It's highly radioactive, so it has to be extracted very carefully, and then shipped to Los Alamos, configured into these small devices, which would have their limited shelf life, and then, plunked into the core of the weapon when you're getting ready to detonate it. And so that was initiator design was apparently a very tricky part of the material was dangerous, it was highly radioactive. You want this thing to function at the exact microsecond when you want it to function, but not beforehand. And so there was a whole chemistry component of the Manhattan Project located in Dayton, Ohio, by the Monsanto Chemical Company that was responsible for the extraction and processing of the polonium, which is not well known. I remember coming across a letter from Oppenheimer to Groves about the summer of 1943, already beginning to lay out specifications for what sort of neutron flux they would need from these things to get a credible detonation. And so that was it was an integral part of the project that had gone on for a good 2 years before Hiroshima.
So this letter was from or to Oppenheimer?
From Oppenheimer to Groves. And even down to the level of specifying the average number of neutrons they'd want to have released during the operation of the initiator. And then deriving from that how much radioactive material you would need in these things. They originally considered radium, apparently, because there's a fair amount of it around, but it's not nearly as radioactive as polonium. And so you could get away with a much smaller mass of polonium than radium in the initiator.
Now I'm interested in seeing atomic time again, because from the photographs, the initiator is exquisitely crafted. They had a jeweler create it. There's some gold casings.
Yeah.
It's remarkable how this is.
Gold would be heavy enough to stop the alpha particles emitted by the polonium.
Yeah, right, right.
They also, apparently from what I've read, considered for the tamper materials of the bombs to increase their efficiencies, using pure gold as a tamper material, and tested that as a possible tamper. And so the notion for these guys of vaporizing a few hundred kilograms of gold was routine. They used other things ultimately, but that, I guess, that was the level at which they were operating.
Can you explain what the tamper was?
Well, around so if we have our uranium or plutonium core, it's advantageous to surround that with a metal jacket, say a few centimeters thick. And this, even if it's not imploded, even if it's just sort of static, like in the uranium bomb, this serves two functions. As the chain reaction proceeds and neutrons are emitted from the core, if you can reflect those back into the core, they have another chance of causing a fission and increasing the efficiency. So you get an efficiency boost just by the effect of this reflection. And simultaneously with that, the core heats up and expands very rapidly. I mean, this thing is expanding at a rate of thousands of meters per second within a microsecond of the initiation of the chain reaction. And if there were nothing to restrain it, it would just blow itself apart very quickly. You'd lose your critical density and you'd have a very low efficiency explosion. And so just the inertial effect of this surrounding shell, which could be several hundred kilograms, retards the explosion, for a minute amount of time to allow a bit more efficiency to build up. So it has both this reflective and inertial property that enhances efficiency. And you can increase your efficiency many-fold, even with a modest tamper. So it's certainly worth the trouble of providing one.
They thought of everything.
That, I would encourage anybody seeing this to read the Los Alamos primer. They had worked out by the spring of 1943, even earlier than that, actually. They were well aware of the concept of a tamper by 1941, and had made estimates of what sort of sizes and masses might be involved, and some rough estimates of the efficiency enhancement. And that's a remarkable document because they anticipated so much of what was going to have to be done in experimental physics and engineering, the theoretical computations. Many things were, yet to be done. They didn't have numbers for many of the experimental parameters, but they had a remarkably clear idea of what sort of experimental program they were going to need to undertake, and sort of ordnance engineering program to make these workable devices. And it's all in about 20 pages.
It's a good recommendation. Is there something else other than the tamper that you want to talk about that they might find in the primer?
Fascinating. In the primer? The primer covers everything. It's like a mini course on nuclear physics. And it helps to have, obviously, some physics background, to fill in the gaps. It wasn't a tutorial document, but it covers everything from the underlying mechanics of the fission process, the energies of the neutrons emitted. It's remarkable how close a call this was, in the sense that maybe that's not the way to phrase it, but as a physicist, it strikes me as kind of fascinating that there's over 2,300 isotopes of over 100 elements are known, have been synthesized and occur naturally, a couple hundred, and many, many hundreds more synthesized. And of all of those isotopes that have been discovered, since Rutherford, only 2 have proven practicable for nuclear weapons. And when one looks at the combination of the physical parameters of the energy needed by a neutron to induce fission, the cross-section, the densities, the spontaneous fission problems, and the window just narrows to these 2 isotopes, one of which occurs naturally but is incredibly rare, and the other of which doesn't occur naturally at all and has to be synthesized by first getting a fission reactor operating and controllable. And so it's, to my mind, a remarkable sort of confluence of factors in nature that, to a physicist, this is just fascinating, that of all of these factors interplay in such a way to narrow it down to this narrow window, what I've come to think of personally as the window of facility. And they were aware in 1943, at the time of the primer, of the possibility that spontaneous fission could trigger a reaction before intended, but apparently the magnitude of the effect of plutonium came as a very rude surprise, and that prompted the whole development of the implosion technique. It was a classic case of something that in theory looked promising, looked good, but then turns out to have some horrific practical complication that made their lives very difficult.
So is this illustrated in the test, the first, I guess that was the hydrogen bomb that was so surprising, that they were so far off
Oh, yeah.
in their estimate.
I admit that's much more out of my kind of area of interest and background, but I gather in that case they didn't anticipate some of the materials in the first thermonuclear weapons contributing so much to the energy release. I think the particular culprit was lithium, which was used in some of the reactions in this thing. And a particular isotope of lithium being more fissile than had been anticipated. Now, I'm going to want to check this out because I probably garbled it up, but and it resulted in underestimating the energy release. The predicted energy release of the Trinity device, there were estimates that were sort of all over the place, but they actually had a pretty good handle on estimating by the summer of 1945 that if the implosion would work correctly, what sort of efficiency they should get. These guys were good.
Yeah. So I saw that slide of the pond cabin where Emilio C. Gray. Yes. Does that tell it like it was? I mean, it's just working with such crude and humble
equipment. Tabletop.
Right.
That is something to me that I think I try to show my students, actually, is James Chadwick discovered the neutron with an experimental vacuum chamber that would fit in your hand. Okay, it would literally fit on the table beside you. Segre must have been doing something, kind of similar. The first prototype diffusion cascade apparatus, would sit in a wardrobe cabinet. So some of these things are, literally handmade devices. Or Alfred Neer's spectrometer that he isolated the first uranium-235 with was a handmade spectrometer, in his lab, made with with a budget of a few $100s. And, he isolates this minute amount of uranium that I guess you could be dramatic and say changed the course of history. The first synthesized samples of plutonium were so small they could only be seen under a microscope. And that had to be scaled up to kilograms. But I think when I was a student, that's what first attracted me to astronomy, was the combination of every scale of energy and size and time comes into astronomy, because stars operate by nuclear fusion. So these minute nuclei of atoms, and yet then you have stars, which are the components of galaxies, which are the components of the universe. And so you can have every time scales, from literally the atomic, the subatomic, to billions of years. And in a way, I guess, the nuclear devices are like that, in that these reactions on these most minute scales, individual nuclei, and yet, have latent in them, in something that would fit, in the size of a softball. Latent in them is so much energy that can be released. That's just staggering. It's easy, a physicist comes to this because of the technical stuff and the computational stuff, but, I've also found that just reading the personal stories of the people that were involved is fascinating. And even if one of your listeners is not a physics student, but a sociologist or an organizational theory student or something like that, some of the personal stories of the people that were involved are just compelling. You can't help but be compelled by the story of an Oppenheimer, and in some ways his own worst enemy, or of Lise Meitner fleeing Germany, and then learning later of the discovery of fission, and or of by the good fortune of Frisch and Peierls ending up in Birmingham and writing their memorandum in the spring of 1940, or Hans Bethe or Enrico Fermi, and just some of the lives of these people are fascinating. They're just endlessly fascinating characters, and then to contrast somebody like an Oppenheimer and a Groves. No writer of a Hollywood drama, they wouldn't have to dramatize it because the story is so good by itself. And this mixture of incredible personalities that you wonder in ordinary life just wouldn't come together. You raised in your discussion with John a little while ago some of the ethical issues in the context of the war and the endless historical debates about the use of the bomb or not. And I think something that's easy to forget is what I've come to think of, this is my own terminology, the theory of nuclear inoculation. That if these things had not been developed when they were and affected the end of the war, perhaps one can debate to what degree the bombs were responsible for ending the war. But I think if they hadn't been used at that time, they could have easily been delayed by a few weeks, any number of problems. And then what might have happened in a later war, when there was more of them, held by more countries, and they were more powerful, if we had not become aware in 1945 just how powerful these things were. And even Hans Bethe has said that he felt that the bombings of Hiroshima and Nagasaki were necessary to help end the war and inform the world of the nature of these things, that they can't be used again. And maybe it has had some deterrent effect over the last 75 years. What might have happened in Korea or somewhere else? I do try to explore some of those things when I put this before my students.
Yeah, no, that's really important. Yeah.
That there's this horrific context. Who would want to be saddled with a decision like that, you know, with an ethical issue like that? But that's what these guys faced, and here we are.
So what do you, are there other things that you try to get your students to think about in terms of today's world?
Well, yes, and so, you know, the relationship between scientists and society, some of the ethical issues of what they do, and there's, of course, there's so many things now where scientific ethics are important. You could think of genetic engineering or geoengineering. Climate change, you know, and so these have just a myriad of technical issues and ethical issues that, you know, they're still very much with us. And you know, this wasn't some remote, abstract sort of thing. This was real people, you know, in their lives, involved in this stuff, sometimes torn by it, and yet in the circumstances of the time, you know, sometimes I ask my students, what would you have done, knowing what you know, had you been in that situation? Say if you were President Truman, what would you think about doing? And that it's, you know, science and physics just isn't this cut and dried abstract stuff. It has real effects. It affects the world. What about ethical issues of artificial intelligence? Their generation will inherit that. Oh God, I'm becoming a sociologist.
It is, as we...
For a physicist, that's...
That's good. Yeah. There's no boundary, although in curricula, they tend to say, here are the humanities courses, here are the science courses, if they're two worlds.
And it's in real life, it's not like that.
Yeah, no, yeah. I know. So it's good you're preparing your students to be broad-gauged.
I hope so. At least they come out, they're often horrified to learn that, okay, you know, maybe some idea, there was the war, the atomic bombings, and they're often just incredibly surprised to find out how big the nuclear arsenals got, how many tests there were, how many nuclear weapons there still are in the world, and they're just astounded. You know, I've had students guess, well, maybe we have a few of these things, maybe they tested a dozen or something, and they're just astounded by the how enormous this became during the Cold War. They often have no, you know, they lived through none of that. They have no experience with it. And that many times there were close accidents. I think, you know, we can hope for a steady downward trend. And, you know, one wonders if they'd ever be eliminated altogether. You can't uninvent this knowledge. You know, but even very conservative military planners say that we don't need as many of these things as we have. We could do a perfectly credible job of security with, you know, with half of what we've got. So.